Next, we have Thibaud Moutard from ESA, caught in the cosmic web, framing the big picture of massive galaxies slow quenching since cosmic noon.
Let's talk a bit about galaxies now. So sorry, you will see that part of the font, I got it wrong because Keynote is not a PDF. So you will see that fonts do not look for acronyms. There is not, okay. It's just a mix up with the font. So today I wanted to talk about something I've been working on lately on mostly CFHT data, but combined with other data. And it's about basically how galaxies evolve and especially how massive galaxies quench their star formation. So how star formation stops in galaxies and in massive galaxies. Okay, so I wanted to start with that because it's funny to notice that basically almost exactly 100 years ago, galaxy evolution study started with this paper from Hubble. So everything was already there except for the spelling of Hubble. But it's just funny. You can find the paper. It's in the news. It's in the New York Times, and you can find it if you want. So So when you look at the sky, so this is a very nice picture. I think that Jean-Charles knows this picture. So it's from Euclid. On this picture, what you see is basically the tremendous diversity of galaxies in terms of their shape, their morphology, their colors. Behind that, you have obviously the stellar mass, but you also see that the environment of galaxies is very different. So here you can see that you have a cluster, the Perseus cluster, and this cluster is connected to other clusters through cosmic filaments. Okay, so this is something I will be discussing today. So galaxies organize in the universe along cosmic filaments, and these filaments connect galaxy clusters together. And the galaxy evolution is driven by the interplay with the cosmic web. Okay, so if you look at galaxies, you can classify them. This is something you know well, but it's good to think about it. So if you want to understand galaxy evolution, you may want to classify them. So on average, it's true that you have ellipticals that are mostly red and dead, so no more star formation in elliptical galaxies on average. And on average as well, you can have disky galaxies with ongoing star formations. But in the local universe, what you can see is you have galaxies that depart from this classification. You have red disks, so disky galaxies where you have no star formation ongoing. And you also have blue ellipticals, so that means elliptical galaxies with star formation. So just to say that things are a bit more subtle than it may appear. And when you look at the fraction of galaxies where star formation has stopped, so quiescent galaxies in the universe, what you can see is that this fraction has evolved and increased over time since the time at redshift 3, which we call cosmic noon, which was the period of time when the universe was the most star forming. And indeed, if you want to understand why the star formation efficiency has dropped since this epoch, which you can see here, can I see? I don't know if I can do something, whatever. So you can see that since this time, indeed, star formation efficiency has dropped. So it's very important to understand why the quenching operates in galaxies over cosmic time. But this story of the quenching does not start since cosmic noon. Actually, as early as galaxies were formed, almost 30 billion years ago, basically 1 billion years after that, you already had the first quiescent galaxies. So quenching, the fact that you can stop permanently or quite long period star formation in galaxies, is something that happens since a very long time in the universe. And this is something I want to explain and understand. So if you look at the quenching itself, so the way to quench star formation, actually it's not a monolithic process. You don't have only one way to quench star formation in galaxies. And this has been discussed over time since quite a period of time. And so what people have seen is that the process that quench star formation in galaxies may be different for low mass galaxies and high mass galaxies. And this is what you can see here. You have several papers discussing that. But if you want to summarize this, I may highlight at least 3 ways to quench star formation. You have a fast process for low mass satellite galaxies within galaxy clusters. Okay, so in these very huge, large structures, cosmic structures. So galaxies will be basically harassed by their environment. You have also a slow quenching process that I've worked on a couple of years ago that is affecting part of massive galaxies at low redshift. So since cosmic noon, basically, since a couple of 8 billion years ago. And you also have now another quenching channel, if you may say, that's affecting galaxies at very high redshift. So those first galaxies I told about, the first quiescent galaxies we observed had barely 1 billion years to form and to quench. But today, what I want to discuss is this quenching channel, so operating on massive galaxies, so galaxies with masses of about 10 to the 10.5 solar masses, and this operates at fairly low redshift, and again, it's a slow process, and since it's slow, it requires time to be operating. So here, what you can see in this diagram, so it's a color diagram, red frame, which is basically NUV minus R minus K, but what is important here is that you have what we call the star-forming main sequence on the lower part of the diagram. So galaxies evolve from the left to the right, and they grow in mass. At the top of the diagram, what you have is the red sequence, so quiescent galaxies where star formation is no more operating. And in between, you see that you have what we call the green valley. So you see that I'm still lost in the green valley a couple of years later. And what is interesting in this green valley is that you see galaxies that are transitioning from the star-forming main sequence to the red sequence. So this is where you want to catch galaxies and understand what's happening to turn them into quiescent galaxies. So, as I said, a slow process, M-star galaxies, so fairly massive galaxies, fairly massive dark matter halos as well, and galaxies that seem to be preserving their disk. So it goes in the same direction that you have a slow process. So now you try to understand what kind of mechanism that can be able to quench the star formation while preserving the disk. So something quite not very aggressive, but able to impede star formation, maybe impeding the cold gas fueling of the galaxy. So, and a couple of years ago, I worked on this, and selecting these galaxies, we could see that they were more likely to host galaxy mergers, but those mergers happen after the quenching started. So the merger itself, or between two galaxies for these massive galaxies, is not the reason for the quenching, but more something that happens after the quenching. So part of the mechanism, but not the reason for the quenching. So the only scenario I could find in the literature to explain that is this picture. So in simulations, you can see that low mass galaxies form far from cosmic filaments and far from walls, but basically far from large scale structures. And those small galaxies are always aligned with the cold gas streams that are flowing towards cosmic filaments. So this is what you see here with the white arrows. So basically, just to say, keep in mind that low mass galaxies that form far from cosmic filaments have a spin that is aligned with their closest filaments, just because there is this interplay with the cold gas streams that are flowing towards filaments. Okay, it's like a waterfall. Okay, but then when galaxies grow in mass via star formation and also mergers along cosmic filaments, once they reach some mass, characteristic mass, they will no more be able to be realigned by the cold gas streams. So interplay with the cold gas streams won't be able to change the things. And they will start to get disconnected also from the cold gas streams. So this is something we want to understand. And maybe this is the reason why part of massive galaxies quenched, being disconnected from cold gas streams. But the thing is that this is simulations. So now we want to see if in observations we can try to validate this model. And the two things we want is that those galaxies should be close to cosmic filaments and they should experience mergers, or their dark matter halos should experience mergers. This is something we can do. So I use the Viper survey, which is now quite old, but it's still unique in its capability to probe the redshift range 0.5 to redshift 1, basically. And you also can see that the two Viper fields, so the two there, they basically, you can see the cosmic web inside. So you can reconstruct the cosmic web. And on the right, you can see the data I used from photometry to get all the physical parameters from galaxies. This photometry is mostly from CFH, but also from Galax. So here you see the reconstruction of the cosmic web, which I will be using. And now what you need as well is to identify galaxy pairs, so the mergers of two dark matter halos. So this is a recipe, we can talk about it later, but basically when two dark matter halos overlap, I consider they are interacting, okay? Overlap in radial velocity, but also obviously on the sky, so in astrometry. Okay, so this is my two fields, and if you overplot the pairs and major pairs, so major pairs are just when two dark matter halos are similar masses. So you see that they follow the cosmic web, so which is okay, something we expected, but by eye, this is what you can see. And this is when you plot the distance to the cosmic filaments from these pairs, and you see that clearly pairs are closer to cosmic filaments than any other kind of galaxy. So clearly you can say that indeed the merger of dark matter halos happens close to cosmic filaments. And now if you want to understand what happens for the star formation of the galaxies, you can look at this diagram. So here you have star formation rate on the y-axis and mass on the x-axis. And in that case, you can see that clearly two things. So I would like to focus on the upper right part. So what you can see is that the distance itself to cosmic filaments is not enough to quench. You cannot say that you have a huge trend, but what is really striking is the fraction of pairs that you have when you have pairs, when you have massive galaxy pairs or in their dark matter halos are overlapping and interacting, you see that they are more likely to be quiescent or in the process of quenching. So clearly there is a correlation there. So if we summarize that, okay, so you can see that, okay, you are on the right, you are a star-forming galaxy, there is almost no pairs of dark matter halos, no interaction between them, and you have star-forming galaxies, but as you go to the green valley, so intermediate SSFR galaxies, you see that the fraction of interacting dark matter halos is higher. So clearly when you have interacting dark matter halos, you have a higher probability to be quiescent or to be in the process of quenching. Okay, so these are basically those two conclusions. So massive galaxy halo mergers are more likely to happen along cosmic filaments, which is something we expect from simulations, but we see that as well in observations. And also the halo mergers and the offset of the quenching of their hosted galaxies appear to be simultaneous in observations. So if you have to pick one scenario, there is this paper from Aragon Calvo talking about indeed how you can detach galaxies and especially massive galaxies from their from the cosmic web and especially from cold gas fueling via the merger of their dark matter hosts halo. So I would say that what we observed is confirming this picture, and this is the conclusion. Yeah.
Okay, thank you very much. Questions?
And you were your I was curious for galaxy quenching. You also sometimes hear about the role of black holes at AGN. as being like another explanation. So I'm curious in the operation or this will play a desert role. Yeah, you could cover that these.
So actually, the first thing I tried a couple of years ago was to see whether AGNs could quench those galaxies. I'm not talking about any kind of quenching, but for example, for the very first quiescent galaxies in the earlier universe, probably AGN quenching is interesting. But for these guys, I could not find any correlation. The only thing I could find was that on the upper right, you see that this is the fraction of different types of AGNs in those quenching galaxies, so on the process. And the thing is that, okay, radio-allowed AGNs are not a solution because they are not in the green valley, but after when galaxies are already quiescent, so it's not causing the quenching. And the other thing is that the AGNs I found in the green valley are not any kind of AGNs. Those are heavily obscured AGNs, and they are tracers of mergers. And again, they happen once the quenching already started. So in my case, it was not a solution.
Okay, thank you very much.